Hello students, again your physics teacher with you, Hassan Darwish. Also, I am going to solve in this video an example about the conservation of mechanical energy and rotation. But this exercise is only for GS students, not for LS, as you see here. So in this example, we have a thin rod AB of length 100 centimeter and of negligible mass, okay, carrying at the extremities A and B two particles, M1 and M2. We have a third particle, M3, can slide on the part OA. This particle here can slide on OA, where O is the midpoint of the rod AB. Now M3 is at point C. Here it is, where distance from O to C is 15 centimeters. Determine relative to O the center of mass of this system. As we learned in the last year, we choose here coordinate system, and as I did in the previous example, I choose here coordinate system. This is x-axis. That's the simplest way to determine G. This is abscissa x, and this is the ordinate axis y. And as you see, all the particles A, C, O, and B are collinear along the x-axis. They don't have ordinate component, right? Okay. So part 1, A. Abscissa of G is equal to OG, position of G relative to O, which is equal, according to the rule, M1 x1, right? Means mass of particle A, abscissa of A, plus M2 x2, means M of particle, say C or B, here, xb, plus M3 x3, means the abscissa of C, xc, plus M4 x4, means mass of the rod, abscissa of the rod, which is O, because the center of mass of the rod alone is at O, over the total mass, clear, over M total. So you have to be careful about the abscissa. It could be positive or negative. For example, for A, the mass of A, 0.3 kilogram. It is 300 gram. But the abscissa minus 50 centimeter means minus 0.5 meter, right? The abscissa of A is negative, plus mass of C 0.4, and it has negative abscissa, minus 15 centimeter or minus 0.15 meter, plus B, mass of B 0.5 kilogram, and the abscissa of B is positive, means 50 centimeter or 0.5 meter, plus, here is the question. Mass of the rod is 0 because the rod has negligible mass, and the abscissa is also 0 because at O, over the total mass, which is 1.2. Now if you do the calculation, you get 0.0333 meter, or 33.3 centimeter. Okay? Or 3.33 centimeters, sorry. That's part A. Now part B. In part B, we displace M3 on OA. We displace this point on the rod here till the center of mass coincides with O. Show that the position of M3 is 25 centimeter away from O. So in B, G coincide with O. It means G is located at O. Means abscissa of G equals 0. So please replace in this equation, we get abscissa of C minus 0.25 meter, right? So the abscissa of C is negative, and this is logical. Clear? Or 25 centimeter. Good. Now part 2. The center of mass of the system being where? At O. This system can rotate about an axis delta perpendicular to the rod and passing through O. So here is delta. Here is delta. You only see the tip of delta. Okay? And C is here now. Why? Because the center of mass is at O, as he said. Determine the moment of inertia of this system with respect to delta. Okay, good. So 2, part A. Moment of inertia of the system. System consists, don't forget, the system consists of the rod. This is I of the rod. Plus 3 particles. A, particle A, particle B, and particle C. Right? But be careful. Here, I of the rod is 0. Why? Because the mass of the rod is 0. So moment of inertia of the rod is 0. Now A is a particle, B is a particle, and C is a particle. And on every particle, the rule is mr squared. Right? mr squared and mr squared. You must know the mass of each particle and the distance of each particle from O. Try to do the calculation. We get how much? So 0.225 kilogram meter squared. Any problem? Now you remember the rule of the moment of inertia and the rule of the center of mass. We will extensively use them, especially in chapter 4 when we study mechanical oscillations. Now let's go to part B. The system is given an initial speed theta prime 0, initially 20 revolution per second at the instant t equal to 0. And at the instant t equal 10 seconds, the system stops in a uniformly decelerated motion due to friction between the axis delta and the rod. We suppose that the moment of the friction force is constant, m. Determine the angular acceleration and the number of revolution. That's part 1. Now you know part B. Here. Since the motion is uniformly decelerated rotational here motion or circular motion, let me call it circular motion, then I apply the rules directly. Theta equal, you have to keep them in your mind, learn them by heart, half theta double prime t squared plus theta prime initial t plus theta initial, similar to uniformly varied rectilinear motion. And also here, theta prime equal theta double prime, just the derivative of the first equation, time derivative. Theta prime 0. Now what do we have in this given? Let's see. We have the time, and we have theta prime initial, and we have theta prime final. Here, when the rod stops, theta prime equal to 0, right? And time is 10 seconds, and we have this initial value. So replace them here to get theta double prime. So here, theta double prime is minus 4 pi radian per second squared. And be careful, you have to change revolution per second, as we did in the previous videos, into radian per second. You just multiply by 2 pi, because one revolution corresponds to an angle 2 pi. Okay? And see here, theta double prime is negative, and this is true, because the motion is decelerated, right? Now let's jump to the second part. Determine by applying the work kinetic energy theorem the value of the moment of friction. Remember, we studied in the previous videos the work kinetic energy theorem, and also we studied the work done by a force and rotation. Remember? Let's do this now. Part 2. Now work kinetic energy theorem. Remember, it is kinetic energy final minus kinetic energy initial equals sum of the work done by the external forces, right? So here, kinetic energy final 0. Why? Because the rod stops. Minus initially, we do not say half mv squared. Be careful, because half mv squared for the particle. And here, half I theta prime squared, because we have rotation. And this is minus half I is calculated 0.225 in the previous part. Now theta prime, also we have changed it into radian per second, 40 pi squared plus equals, work done by friction. You remember the rule, moment of the force times angle theta. We should have calculated theta in the previous part. We forget this. Now moment of the weight, work done by the weight is 0. Why? Because the point of application of the weight is not changing. And also the work done by the reaction of the axis is also 0. Why? Because the point of application of the reaction at point O is not 0. Is not displaced while the rod rotates. So we calculate theta from the previous part, and then we get moment. Let's do this. So if we have calculated theta, it is 200 pi. Now replace here, you get the moment of the friction force 2.83 Newton meter. Okay? This is everything about, you see in this example we have applied the work kinetic energy in rotation, and we have learned or remembered the moment of inertia of a system, the center of mass of a system. Okay? See you in the next videos. Take care. Bye-bye.